All right, welcome back again, everybody. Today we're going to be covering section 8.7, and this is actually the last section of the course, so you made it. We're going to be talking about the cross product, which is basically another operator for vectors. So let's get started. Pull up the slides. There we go. All right, so last time we talked about the dot product. This time we're going to talk about the cross product. We're going to start with a motivating question just to kind of figure out what we're doing and what we're looking for and why we're doing it. Then we're going to get the definition of the definition of the cross product. Then we'll talk about geometric results, and then we'll finish up with properties of the cross product. So, motivating question. Here's the beginning. If we're given two vectors in V3, how can we find a third vector that is orthogonal to both? So remember, orthogonal means at a right angle or perpendicular, right? So this is the motivating question. If we've got two vectors in 3 space, how can we find a third one that is perpendicular to the other two? And that's what we're going to do. So to answer this question, we're going to have to do a little bit of algebra. But let's start with let's start with 3 vectors. So let's start with the vector A and B. And we're going to let C be a vector that's orthogonal to both of those vectors. All right, that's where we're going to pick up. Let me highlight these. We got A, we got B. C is going to be the vector that's orthogonal to both of those. So if C is orthogonal to both of those, then it must be the case that the dot product of those vectors with C is going to be 0, right? We proved that in the last section, that you're orthogonal if and only if the dot product is 0. So when we compute the dot product just using the definition, we get these 2 equations right here, just like so. So what we're going to do now is we're going to proceed to calculate what C1, C2, and C3 must be. So in other words, if C is orthogonal to A and B, what are the components C1, C2, and C3? We're going to calculate them right now. So here's how we do it. The first thing we're going to do is we're going to solve the system of equations. It's a system of 2 equations in 3 variables. So what that means is we're only going to be able to solve it in terms of the components of A and B, which is okay, because that's really all we want, right? We want to be able to, if given the components of A and B, find a third vector that is orthogonal to both of those vectors A and B. So we're going to solve this system of equations. Here's the first step. We're going to use elimination. So maybe you remember this from like an algebra class you took in the past. But what I'm going to do is multiply the first equation by B3 on both sides and multiply the second equation by negative A3 on both sides. And so then we'll get this result right here. That's after the multiplication has occurred. Now we're just going to add those 2 equations together and we will get this. So if you want, you could pause the video and look through the calculations more clearly or with more detail, but this is what it'll be right here. Now, the thing about this is this equation here has a very nice form. So it's in the form PC1 plus QC2 equals 0. So basically this piece right here is P. Can do better than that. There we go. There's P. And then this right here is Q. Now, it turns out that any equation that has this structure, like P C1 plus Q C2 equals 0, it has the solution C1 equals Q and C2 equals negative P. So basically take the opposites of both. So let P be, right, like let P be negative C2 and so on, and that will give you 0 in the end. So because of that, that tells us that C1 is equal to this and C2 is equal to this. So now we've already got 2 of these components. We got 2 of the components of our orthogonal vector. Now the next step is we're going to take those 2 components, we're going to go back to the original equation, we'll just use the first one that we started with, and we're going to substitute those results into that first equation and then solve for the third component. So the first equation was this. This is what we got when we dotted A with C. We got this right here. Now we're just going to replace C1 and C2 with the results we just obtained. So there's C1, there's C2, and then we're going to solve for C3. At this point, it's really just a lot of arithmetic, so distribute the A1, distribute the A2, you can cancel some terms that are opposites of each other, then you end up with this line right here. And then from that, you can basically factor out an A3 and cancel it. And then you're left with this. And then when you solve this for C3, we get that for C3. And we did it. We did it. So now that we have the first two components, we had the first two components, now we have the third component. So a vector C that is perpendicular to both A and B is this vector right here with these three components. There we go. All right. Don't worry, we're gonna come up with an easier way to remember this formula, but that is the vector itself. And again, you can look back through the calculations. It's definitely perpendicular to both. And if you don't believe it, which you shouldn't, you can always just dot it with both vectors and see what you get. And it'll be zero. It'll be zero for both of them. So this is actually how we define the cross product, which is also called the vector product. So the cross product or the vector product of two vectors, A and B, is the vector A cross B, and it's given by these three components. So this is the definition. And this is like a new symbol that we're using as our new operator. So it's the times symbol. It's just like a straight crossed X, and that stands for the cross product. Now, a couple things to take note of. The cross product of two vectors is orthogonal to both. That's the key thing, right? So when you talk about the cross product, you were talking about a vector that is orthogonal to the two things that are the factors of the product. That's what that thing is. So even though it has this structure, it is still a vector. That's the next point on that list. It's a vector, and it's a vector that's orthogonal to the two factors of that product. All right, so that brings me to this important point right here. Note very carefully that the cross product is a vector, but the dot product is a scalar. So these are not the two same operations, and they are producing two very, very different things. The cross product is a vector. A vector has length and it has direction. The dot product is a scalar. Scalar is just a real number, basically, right? So these two ways of multiplying vectors are very, very different, but they give us a lot of really, really interesting things. That's one of the fun things, right? Vectors are like a new mathematical object that we developed a couple sections ago, and now we can talk about playing with those objects, playing with these vectors. And we found two new forms of multiplying these vectors that give us really interesting information. We're going to see more about it in just a minute here. Another important point, and this is the only time I'll say this in all these sections here, the cross product is only defined when the vectors are in V3. So what we just calculated, what we just computed, all the results that we're talking about today, it only works in V3. So it only works in 3 space. So that means that the cross product is not defined for two-dimensional vectors. So if you've got a vector that's in the plane, you cannot find the cross product of it. Really, if you think about it, if you've got a vector in the plane, like the xy plane, a vector that would be orthogonal to both, or sorry, if you have two vectors that are in the plane, a vector that would be orthogonal to both would be like popping out of the plane, right? So you need like a new space to make that possible. So this particular operation and this particular result is only defined in V3. However, however, you can actually generalize this using the concept of an exterior product and exterior algebras. So if you want to read up on that, just click on that link and that'll take you to the Wikipedia page. And basically you can generalize it, but it gets very technical and very complicated. But there is a way to kind of generalize it to higher dimensions. For us, we're going to stick with V3 for the cross product. All right, so in order to make this definition easier to remember, because this is a lot to remember, and I am not a big fan of memorization whatsoever, especially when the things you have to memorize are all just like slight variations of each other, which this is. I hate having to memorize that stuff. Don't try to memorize that stuff. I wouldn't trust you to memorize this stuff. So it's nice when we can have a shortcut that lets us figure out what it should be without having to remember. And we're going to do that here with what we call determinants. So we're going to introduce this new object called a determinant and see how it works for a minute. All right, so a determinant of order 2 is defined as this right here. So these are basically just two vertical bars that are indicating that you're taking a determinant And really what's inside here is a matrix. It's a 2 by 2 matrix. And many of you are going to study matrices when you get to linear algebra. But the determinant is defined as basically doing this product, A times D, and then subtracting B times C. So AD minus BC, that's basically what the determinant is. A determinant of order 2. It turns out that determinants can be of any order. So again, this is something that generalizes to any dimension. But a determinant of order 3 is defined in terms of second order determinants. So let's say you had a 3 by 3 matrix, which is what we're going to need to compute our cross products, right? Because we're working in V3. So the way that you compute a determinant of order 3 is you basically select one of the top rows, or select a component in the top row, and then compute the determinant of the piece that gets canceled out. So it's almost like if you select A1, forget A2, A3, forget B1, C1, and then compute this determinant right there. There you go. So you're going to do A1 times that 2 by 2 determinant. Then what you're going to do is repeat that process, but you're going to move over. So now instead of doing A1, come here, we're going to do A2. We're going to forget about this, and this. So basically forget the row and column that A2 is in, and then we're going to do a determinant with these as the columns. So B1, C1, B3, C3. And we're going to do A2 times that. So one thing I want to point out here is it's A1 times that first determinant minus A2 times that second determinant. And then the third term is going to be A3 plus the last 2 by 2 determinant that you get. So now we'll pick A3, forget about the row and the column associated with A3, and then do the determinant of that 2 by 2 matrix. And then you're going to add, subtract, add. All right. So this is what determinants are, and we're going to use this notation to help us remember the formula for the cross product. This is, as weird as it looks, this is going to help us remember if it's like A2B3 minus A1B3 or whatever, all that stuff. So here's how we're going to remember it, and this is what you need to remember. This right here. So this is what the cross product is. So we're going to kind of, I mentioned it down here, but we're going to kind of cheat a little bit, and we're going to say that this is the ith, or this is the basis vector I, this is the basis vector j, and this is the basis vector k. And how do we remember what the cross product is? We're just going to use that formula for the determinant, the 3 by 3 determinant, and then write it out. That's pretty much it. So you do I times this determinant, then you're going to do j times this determinant, and then you're going to do k times this determinant. And that's how you can remember it. And then you're going to get determinant times I, determinant times j, determinant times k. And that's a good way of remembering the formula for the cross product. And remember that each one of these two-dimensional determinants is computed by doing this minus this. So A2B3 minus A3B2. And that should be the first component. There we go. A2B3 minus A3B2, and so on and so on. Okay, so a couple points to note about this this handy mnemonic almost to remember these. Notice the alternation in the signs of the terms. So there are 3 terms here. There's this one, and this one, but the signs alternate. So it's like minus plus, minus plus. That's what's going on. The other thing I will say here is that technically this is what we call an abuse of notation, since when you learn about determinants later, determinants are actually real numbers. So this is a little bit of an invalid use of the determinant notation, because these aren't technically determinants, but the structure of a determinant matches this perfectly. So we abuse this notation to help us remember how to do this. That's what it is. So the takeaway from all of this is that this really is just a handy guide for computing a cross product. So it's a little bit hand wavy where I'm like, oh, we're going to use this thing. That's not really how you use this thing, but we're going to do it anyway. This is really just a shorthand to help remember how to compute a cross product. That's all I mean. Okay, so let's try it. And I want you to try this one on your own, and then we'll do it together. So let me pull this up here. See if you can find a vector that's orthogonal to these two vectors. Remember that it's going to be the cross product. So try to compute it on your own, and we'll do it together. All right, now let's do it together. So we're going to use that handy shorthand. We're going to write this 3 by 3 determinant here. Notice what I've got is I've got the basis vectors in the first row. And then below that, I've got the first vector A. And then below that, I've got the second vector B. Then the formula for determinants basically says do I times this determinant, which is right here. Then subtract J times this determinant, which is right here. And then add K times this determinant, which is right here. There we go. Then remember that for 2 by 2 determinants, you basically do this minus this. And so when we do those products and those differences, we're going to get this times I minus this times j plus this times k. Do the simple arithmetic, and you'll get negative 23, negative 1, 15, and that's the vector. That's the vector that is orthogonal to both in V3. There we go. You could also write it equivalently as negative 23, negative 1, 15, but you don't have to. They're both the same. And that's it. Cool, huh? So if you can remember that determinant structure, cross products are actually very, very quick to compute. It's not too bad. Now, there is one issue that we have to address, which is the cross product is a vector. And it's a vector that's orthogonal to both of these vectors, or both of the vectors that you give it. But it's orthogonal in which direction? Does it go up or does it go down? And nicely enough, it turns out that the right-hand rule helps us determine or tells us which direction it's going. So you use the right-hand rule again, just like you did when we were talking about three-dimensional space. And if you've got a vector A and a vector B, and you've got this angle between them, then it turns out that the cross product of those two vectors will be perpendicular in that vertical direction, or in like almost like the positive z direction in some sense. But remember, these vectors are not necessarily parallel to the axes. These are just two random vectors in V3. But you basically just use the right-hand rule again, and the direction of your thumb tells you where A cross B is going to be pointing. And that's it. That's the idea. So everything nicely fits together, right? It's pretty cool. Okay, now we get a really, really interesting result. And I hope you can appreciate how similar it looks. It's kind of cute. So if theta is the angle between the two vectors A and B, meaning it's between 0 and pi, then it turns out that the length of the cross product, the length of that vector is given by the formula, is given by the formula length of A times length of B times sine of theta, which is interesting, right? So it's similar to the dot product in that sense, that it's like the length of A times length of B. I'm sorry, it's the length of A cross B, and it's just length of A times length of B times sine theta. The difference here is the dot product was just a scalar, and it was length of A times length of B times cosine theta. So a little bit different, but that's what it is. Let's see the proof here. A second here. I gotta share. Let me do this. Okay, there we go. That'll help a little bit. Then, maybe I can do this. Okay, there we go. Let's see the proof. The proof is pretty nice. I'm sorry, the proof is not pretty nice, but the proof is pretty straightforward. It's just a lot of messy arithmetic and stuff like that. So if you use the definition of the cross product and the definition of vector magnitude, we get this. So remember, the length of a vector squared is just going to be this. So there's the first component squared, second component squared, third component squared. Then at this point, all you can do is literally FOIL everything out, multiply everything out, and then you can combine some like terms and so on. And then it turns out that you can actually factor the result. So this is one line right here, one long line of calculation, and you can factor the result. When you factor it, you're actually going to get this times this minus this squared. Now, the first two factors are the length of a squared and the length of b squared. And then this right here, that's the dot product. That's the dot product of a and b, right? That's the dot product of a and b squared. So we can write it as the dot product squared. Now, remember that we can re-express the dot product in terms of cosine of theta, the angle between, right? So when we do that, we're going to get this. Remember, A dot B is equal to length of A times length of B times cosine theta, right? So we're going to get the same thing, but all squared. All of that squared. And now, check this out. These two terms have a common factor of length of A squared, length of B squared. So we can factor that common factor out, and we get length of a squared times length of b squared times 1 minus cosine squared theta, and there's that Pythagorean identity popping up again. So remember the Pythagorean identity, cosine squared plus sine squared equals 1. You manipulate it a little bit, you get 1 minus cosine squared is equal to sine squared, and that's the proof. Oh, I forgot to put the little box. I should put the little box over here. There we go. End of proof. So, oh, I'm sorry, we're not done with the proof. There's one last step. I just realized all we did was we showed that the length of the cross product squared is equal to that result squared. So here we go. Now, because sine of theta is positive when theta is in this interval, that means that the square root of the sine squared theta is just going to be sine of theta. So you have to be a little bit careful with that, algebraically speaking, because normally taking the square root of a square gives you the absolute value. But in this case, because we know that sine of theta is always non-negative, the absolute value will just be positive anyway, or non-negative anyway. So we just get sine theta, and the square root and the square cancel out, quote unquote. So in other words, you can take the square root of both sides, and you'll get the result. Boom. That's the end of the proof. There's the little square. Okay, nice. All right. So now we've got this new cross product. It's this vector. We know how to find its length. And this is the definition. So this is like putting everything together and just restating the definition and putting it all in one space, basically. So if we're given two vectors A and B and R3, then, or I should say V3 actually, this should be a V, V3, then A cross B is a vector that's orthogonal to both, whose orientation is determined by the right-hand rule, and whose length is length of A times length of B times sine of theta. Okay. All right, so now we get a really handy corollary. And again, there's this really nice parallel between the dot product and the cross product. And yes, that's a bit of a pun. So it turns out that two non-zero vectors are parallel if and only if their cross product is the zero vector, right? And that kind of makes sense if you think about it, right? Because the cross product is a vector that's orthogonal to both. So if those two vectors are parallel, then the only vector that would be orthogonal to both would have to be the zero vector, and vice versa. And that's what we're going to prove right now. So here's the proof. It's actually quite quick. So two non-zero vectors are parallel if and only if the angle between them is 0 or pi. That's like parallel vectors. They're basically like the same, they have the same, I don't want to say same direction, but they're parallel. They just might be opposites of one another. In either case, sine of theta is going to be equal to 0 because sine of 0 is 0 and sine of pi is 0. So that means that the length of the cross product has to be 0. The length of the cross product has to be 0 because of that formula that we just derived right here. Okay, but the only vector that has 0 length is the 0 vector itself. So that means that the cross product has to be the 0 vector, and we're done. So the dot product lets us talk about orthogonality and perpendicularity, and the cross product lets us talk about parallelism, at least in V3, which is kind of cool. All right. Now we're going to get some geometric results. So now we've developed this, we've kind of seen a formula for it, we've seen how to find its length and so on. Now let's look at some geometric results that follow from this. And some of them are pretty cool and they're pretty insightful. So first is the cross product. Oh, the cross product is the, hold on a second. I think I have a typo here. I have to rethink what I'm reading here. That is the area of the parallelogram. The, oh yeah, sorry. This is, I have to rewrite this. Let me rewrite this piece right here. Okay, so I will just say, wait, maybe I can cut this and do this. The length. My apologies. There we go. So this is the result. The result is that the length of the cross product is equal to the area of the parallelogram formed by the two vectors A and B. So this is kind of an interesting result, and you're going to use it a lot in Calc 3. So when you start doing like surface integrals and things like that in Calc 3, you're going to use the cross product because you're basically going to use the area of these parallelograms. But as it turns out, the length of that vector, the length of that cross product is equal to the area of the parallelogram that's formed by the two vectors that you put into the cross product. So grab this right here. So here's B, here's A. And remember, any two vectors can form a parallelogram. You just do this, right? So whatever the area of that parallelogram is, it turns out that that's also the length of the cross product, the length of the vector that's orthogonal to both. The proof is pretty straightforward. You just use a little bit of right triangle trigonometry. You can kind of see it right here. If we want to know the area of this parallelogram, it's the same as that of a rectangle. It's the base times the height. But the base is this, whatever this length is going to be, and the height is this right here. And to find that height, you use right triangle trigonometry because remember sine of theta is opposite over hypotenuse. So sine of theta is opposite over hypotenuse. And then when you solve for that height, you get length of b times sine of theta. So that means that the height is length of b times sine theta, and we have length of a times length of b times sine theta. That's the length of the cross product. So that's pretty cool. So the area of that parallelogram is the length of the cross product, which is pretty nice. All right, now this one I want you to try to do on your own, and then we'll do it together. So find a vector orthogonal to the plane that passes through these 3 points. And I'll give you a bit of a hint before you get thinking about it. You've got 3 different points, and if you want to find a vector orthogonal to the plane that passes through those points, you're going to need to use the cross product, which means you're going to need vectors. So that's my hint. See if you can find 2 vectors that you can find a vector that's orthogonal to them. All right? So think about how you would do that for a minute. All right, now say something out loud to yourself about how you would start. For example, how would you find 2 vectors if you're given these 3 points? All right, now try to work it out on your own, and then we'll do it together in just a moment. All right, here we go. Okay, so we've got 3 points, but if we want to talk about orthogonal vectors, we need vectors. But what we can do is we can basically pair off these points to find 2 vectors. So that's the first step. We're going to pick 2 points pairwise, and we can form 2 vectors with the same initial point. This is something we talked about back in 8.4 and 8.6. So the vector going from P to Q, maybe I'll draw a little picture here. We basically got a couple of points here. Let me do this. Here's P, here's Q, and here's R. So we'll do this vector and this vector. Maybe I shouldn't make them so close to each other. Move this up a little bit. Here we go. This vector, this vector. So how do we find the vector PQ? We just do the subtraction of the components, do the subtraction component-wise, and we get the vector -2, -3, 1. And then we'll do the same thing for the vector PR. 2, 4, 2 is what we get when we compute that. So now we have our two vectors. Now we just need to compute the cross product of those two vectors. So here we go. We'll use that determinant shorthand so that we can compute it without having to remember exactly what it looks like. When you do this computation, you should get this minus this plus this. And then when you go through the arithmetic, you should get -10, 6, and -2. So this is a vector that is orthogonal to both of the two vectors that we just calculated, which means that it's orthogonal to that plane. And in fact, that's how you can find vectors that are orthogonal to planes. Those are often called normal vectors, but you'll learn more about that in Calc 3 and beyond. All right, now, what is here? That's right. Okay, so when we look at the cross products of the basis vectors, we can see some interesting results, cute results, I will say. And this can help you visualize the right-hand rule to see like why it's working or why it's true. So if we do I cross J, turns out we get K, which is good because if we did like I cross J, that's kind of like saying the x-axis cross the y-axis, we should get the z-axis, right? Well, and the positive direction of the z-axis should be the direction that you would get when you turn to the, I guess, to the left from the x-axis to the y-axis, doing the right hand rule. Same thing if you do all the others, right? So if I did the y-axis cross the z-axis, I get the x-axis. And if I do the z-axis cross the x-axis, I get the y-axis. Really, these are vectors. So when I'm saying axis, it's not precise really, but they're vectors. So we're talking about vectors that are parallel to these axes in the same direction as the positive direction. But notice this, if we switch the order, if we do j cross I instead of I cross j, we get -k, because that'll be the negative direction of the z-axis. And then similarly, if we do k cross j, we get -I. And if we do I cross k, we get -j. That's right. So this is actually working. This is giving us the correct vector that we expected. It's following the right-hand rule. Everything is lining up perfectly. But there's a very important result that we just kind of showed from this, which is this. The cross product is not commutative. So what that means is A cross B does not equal B cross A. So we don't have that nice property like we had for the dot product, right? The dot product A dot B was equal to B dot A. You got the same result no matter what. There was no opposite or anything like that. Not the case for the cross product. The cross product does not commute. So you can't move those things around when you're crossing those vectors. You'll get the opposite of the result. So you got to be a little bit careful. Now, similarly, we get, sorry, this is just another note. This is actually related to what's called the quaternion number system. And the quaternions are actually a generalization of the complex numbers to 4 dimensions. So if you really like the complex numbers, and if you really are liking this stuff, you might want to read about the quaternions. So you can click that link. It'll take you to the Wikipedia page for it, and you can like go down that rabbit hole. But yeah, it's this basically is related to the quaternions, and I'll just leave it at that. Now notice this as well. So we're gonna switch some things up a little bit. If we do I cross j, well remember I cross j is just k, and if we do I cross k, we get -j. However, if we first crossed I with itself and then crossed that result with j, well, remember I cross I is going to be 0, because if you cross a vector with itself, you just get 0. And then 0 cross j is going to be 0 as well. So wait a minute. This means we didn't get the same result when we changed how we associated the cross products. So in particular, the cross product is not associative. So what that means is if you've got 3 vectors, A, B, and C, and you do A cross B, then cross C, that will not give you the same result as if you did A and then crossed it with B cross C. So the cross product's not commutative, it's not associative, so you don't have those niceties. Oh well, what are you going to do? Okay, so if that's the case, what kind of properties do we have for the cross product? And we can summarize them all right here. So if A, B, and C are vectors and K is a scalar, then we have a couple of things. So it turns out that A cross B is equal to the opposite of B cross A. And we saw that a couple slides ago when we were looking at the basis vectors. So if you switch the order of the cross product, you're going to get the opposite result. That's what that means. One of the nice things is scalar multiplication can be moved through the cross product. It applies anywhere you want, so that's very nice. So you could do a scalar times A before you cross, or you could do the cross and then multiply by the scalar, or you could multiply B and then cross that result. Those are all equal. So scalar multiplication passes through the cross product, just like it did with the dot product. So that's quite nice. Another nice thing, the cross product is also distributive. So if you do A cross a sum of two vectors, that's the same as doing A cross the first vector plus A cross the second vector, which is pretty cool. So you do get some like scalar multiplication niceties, and you do get a distributive property, which is also very nice. It also because remember the scalar product, or I'm sorry, the cross product is not not commutative. We actually have to verify that there are two different distributive properties. That's the next one here. So notice here we were doing A cross B plus C. Now we're doing A plus B cross C. Because remember, we can't just change the order of those two of that product, right? We'll get something different. So it turns out that the distributive property works both ways, which is nice. So you can distribute from the right or you can distribute from the left, and everything works out nicely. This is an interesting result. So how does the cross product and the dot product, how do those two things play together? So they play together in some interesting ways, and they're not so straightforward. If you want to read the proofs, you'll see them later on in like a Calc 3 course, but check out number 5 and number 6 here. If you did A dot B cross C, it turns out that that's actually equal to A cross B dot C. So it's kind of like the operators switch order, which is a little bit bizarre. And then this next one is even a little weirder. But if you do A cross B cross C, you can actually write it without any cross products at all. You can write it in terms of dot products, and it's going to be this: A dot C times B minus A dot B times C. So that's what happens when you have like a two cross products that you multiply in sequence. One thing I'll note here, so this is why it's really, really important to remember what objects we're working with, and it does take some practice. The cross product is a vector. The dot product is a scalar. So writing something like this right here, it might look weird, but it makes sense because A dot C, that's a scalar. It's just some real number, right? It's 2. There you go. It's 2. So it makes sense to talk about this thing times B. That's just like 2 times B. That's really all it is, because the dot product is a scalar. So there you go. So if you want to do this, you can basically convert cross products to something with dot products instead. All right, so some very interesting properties. The cross product is very different from the dot product, but it's a really, really helpful tool, right? We can find vectors that are orthogonal to two other vectors if we're in 3 space, which is really, really handy. And you're going to use it a lot when you get to Calc 3. So I hope you remember it, and you should review it when you get there. But that is it. That is it, everyone. Congratulations. This is the end of the course. You made it all the way through trigonometry and got a whole bunch of new information. You should give yourself a pat on the back and just appreciate how much you have learned this semester. It really is a lot. This is a lot of stuff. And so I like to leave you with a quote from my favorite mathematician, George Cantor. And he would always say that the essence of mathematics lies entirely in its freedom. So I hope that maybe through a little bit of what I've been saying this semester, you've seen that mathematics really is very creative and there's a lot of intuition behind it. And like I said way back at the very beginning of the course, which I'm sure none of you remember, but you should demand intuition for these things. You should demand intuition. You should be asking yourself why do I care about these things? All of that, right? So From now on, when you go through your math courses, just ask yourself, what's the intuition behind this? Why should I care about this? What can I use this for? Make it make sense to me, all right? And hold your professors and your future instructors accountable to that, okay? All right. Oh, this is good timing because it looks like my slides are about to crap out on me. So I'll end it here. Have a good one, everyone, and I'll see you in the future, I hope. I hope I see you in a later math class. Have a good one.